Okay, so today I'm presenting on almost verification of programs with concealed components. This is me, Sumit Lahiri. I am a PhD student at IIT Kanpur, working with Dr. Roy. Okay, yeah. So here I show an example of a program that contains concealed components, especially the calls to external functions like var and foo. The concept components could be like calls to some web-based service or cloud services, could be calls to external functions, doesn't write in your computer, or it could be calls to ML models or neural networks. We'll have to just retrieve back the values that have been called. Now, given this context, the formal semantics of such concealed components are not known, so verification becomes very hard for such programs. We kind of divide the concealed components into three parts. One which are absolutely unknown, we have no idea what the behavior is, we have no semantics available for them. Others are somewhat easier to deal. These are executable oracles. We can talk about their input-output behavior. And the last one, that's slightly different from executable oracles since we don't have the exact execution semantics for them, but we can model the output from these components as some probability distribution, the kind of outputs that we get from these components. Uh, However, for today's talk, I'll omit discussing on unknown oracles and I'll start off directly with executable oracles. I'll be first be presenting our first work on almost correct invariance. It got published in ISTA 2022 this year. And the next one is symbolic execution for randomized programs, which got accepted this year in ISTA for this very session. Uh, So what exactly is almost verification? It's akin to regular verification, but here we have to deal with programs which have concealed components. So we want to check if some property holds for these programs. If we run the program with all inputs, given the concealed components are already present in them. So with this, I'll first present the work on almost correct invariance, where we synthesize inductive invariance by fuzzy proofs. These are programs that contain opaque components. If you see the program here on line number 7, we have a call to this function named built-in CTZ. So this is a program that is repeatedly adding in order to simulate multiplication. So the task here is that we want to find out an inductive invariant for this program, which can prove that it is correct, given the pre and the post conditions that we have. Existing tools don't really work with this program well because we don't have the logical encoding for this built-in CTZ function on line number 7. However, our tool named Usher is able to uh, find out this invariant for the given program, which turns out to be the correct invariant. Formally, the problem statement that we proposed is that given a specification, the phi, the post preconditions and the program P can be automatically synthesize inductive invariants where P may contain concealed operations. These inductive invariants would establish the correctness proof for the program. Here we resorted to a learner-teacher architecture where the learner would propose a new invariant and the teacher would generate a counterexample if it's wrong, else returns that, okay, it's correct. What we did is that we took the specifications along with the program and the candidate invariant from the learner, converted it into a non-deterministic program. Now, the way we encode this non-deterministic program is that it contains a few goal points, and the way proof fuzzing works is that if any of the goal points in this non-deterministic program, which is a proof of the actual original program P, if any of the goal points is reachable, then we say that the invariant is incorrect for the given program and the specification. However, if none of the goal points are reachable for a given invariant, then it can be deemed almost correct. How do we check for reachability? Because we want to reach these goal points if we had. We use a fuzzer. So this fuzzer is actually able to execute the oracle and say about the input output behavior of the model. So the abstraction for reach oracle is using the Colossus, AFL, and Honkers. So these are a few of the tools that we use for checking the correctness of the header file against the invariant. If the each article returns back with a counterexample, we give it back to the learner so that it can propose another invariant. However, in the case where no counterexamples are produced, we just say that okay, it's probably correct, so it's an inactive invariant for the program. In order to test our tool, what we did is that we took some real-world examples which contained a lot of concealed components, especially components that are hard to reason about. We don't have the formal semantics available. So these are the benchmark suits we took up. There are 15 examples here. And I do the type of opaque operations that are present in these programs, the time it took to generate the invariant and the number of counter examples it took. Interesting example here is this example number 13, which makes a call to a convolutional neural network to like work with the program. So, for example, number 13, what we did is that we considered this array. This array contained about 100 elements. Each of the rows, each of the rows having zeros, ones, twos, threes, and it would basically sum over this complete array. And what we wanted is to have an invariant which says, okay, what exactly sum is for the given program. Our tool Albiet was able to generate this invariant for this program, which showed how effective it is on programs with these components. Here, just for comparison with other state-of-the-art tools which were already present, we took up Code to Win. Code to Win had 113 benchmarks in total. Sorry, 133 benchmarks in total, out of which Code to Win itself was correct on 92 of them. However, with Usher, we were able to have 100 correct examples or 100 cases where the correct invariants were synthesized, and for 5 of them they were wrong. So to further enhance how Usher works, we took these 5 wrong examples and we tried to use a better backend. Instead of doing fuzzing, we employed a mixture of fuzzing and symbolic execution by using Colossus, and we were correct on 102 of them. So 2 wrong got converted to correct ones. Finally, I would like to conclude by saying Achal is available on Doctoral and Zenodo. This is the QR code. I'll now go on to the next work where I talk about almost verification with stochastic oracles. These are oracles where the outputs of these oracles could be modeled like a probability distribution. Here I present the example of some randomized programs. So these are the kind of programs that we're targeting, where we have got a sampling statements. These sampling statements are what are the concealed components, and we have probabilistic assert statements. Like you can see line number 8 and 11 here. So we want to check for these programs. We resort to probabilistic inference, where the objective is that does some property xi hold for these programs with some probability, and we want to find out with what probability it holds for the given programs. Formally, the problem statement that we pose is that given some program P, we run it with inputs X, and the output is a distribution mu, then with what probability does xi hold given we have V? And because this quantity here is not really bounded, so we try to bound it by saying that, okay, instead of getting the exact probability, can we find some bounds? Maybe it lies between some values. So f of x is basically a function over x, and it would give us some bounds. So can we prove it under some bounds that the assert holds? So what we did is that we extended regular symbolic execution to its randomized or probabilistic version, and we built a tool named Inco on top of V. This is an example of Monty Hall. This is a classical example where we have the symbolic execution tree, which looks like this. The blue one encodes the path condition, which I show in the bottom. Given this is the symbolic execution which would happen in a regular setting. However, for our case, what we did is that we introduced new kinds of symbolic variables. These are known as probabilistic symbolic variables, to which we would attach information about the kind of distributions that they were being sampled from and the kind of values that they can take. So we would have both the distribution map and the probabilities which would happen at each program point. Uh, okay. Earlier, if you see in the slides, we would have only symbolic variables alpha and beta. However, for probabilistic symbolic execution, we would also introduce a probabilistic symbolic variable delta. So now the tree can actually fork and grow on delta as well. So and given that we have this probabilistic variable, we want to find that all the winning paths they have a probability of 2 by 3 under the condition which is shown here. So we want to find out the probability for all the green paths that are marked in this tree. These are the results that we had. There are a couple of benchmark examples that we took up from various open source repositories and from earlier papers. These are randomized programs, and this is the kind of, the size of the programs, along with that, these are kind of times we took in order to verify the asserts that we had. In conclusion, what we would say is that regular symbolic execution, so whatever problems we face in regular symbolic execution, like path explosion and other things, they were carried forward in our method. However, we did try to tackle it with some path optimization techniques. But however, there is still scope for optimizing symbolic execution. We can be faster or work on larger randomized programs. We do present info here. These are the links. And we are giving a talk on symbolic execution for randomized programs. That's here on Friday, 9th of December, from 4 p.m. in seminar room G007, where we talk in more details as to what the approach is and how to work. So I urge everyone here to be attended. Finally, I would like to conclude by saying the next area that we tend to explore is, can we extend such almost verification to unknown oracles, something that I alluded in this talk, or can we scale our techniques to larger randomized programs and to bigger probabilistic programs? And finally, can we improve since we are using fuzzing for executable oracles, can we improve the existing fuzzing techniques which work better with almost verification application? With that, I would like to conclude my talk, and I would like to thank TCS Research and ACM Sigman for funding my work and my travel.
Yes. So what do you think the challenges are for scalability?
So one of the challenges that we faced, especially for randomized programs, is that symbolic execution would not scale. Especially if we had large number of paths, we would end up exploring each path, and that would take a lot of time. So we did propose a technique where we try to filter some paths, saying that okay, like some paths are not, they have very less probability. So why even care about those paths? Can we just discard them? But like we do have to come up with better metrics at saying that okay, which paths to discard. I think that may be some more work to be done.
Is there any opportunity for static analysis to discard the paths?
Yes.
Static analysis, can that be applied to discard?
Yes, absolutely.
The low probability paths?
Yes, yes. So I think that is a promising direction to explore. Like how can we improve? Yes.
So like in the probabilistic setting, you've got these assertions. Is there any evidence that programmers can even write those assertions? I'm not trying to sound disparaging programmers. I don't know if I'd be able to do that sort of quantitative reasoning in my head that's required to figure out the probability that a particular assertion should be, right? Like I'm really intrigued by this idea of like, what is the right assertion language for probabilistic programming. Right? Have you guys had an experience with that? For examples, or is it just accepted that that's just how it's done?
Actually, I'm the kind of benchmark that we try to see here. I mean, some of the so some of the asserts were known that, okay, like, can we say that, I mean, especially for Monty Hall, okay, like, there is a higher probability of winning the car if the person switches. So can we, so given such, like, even though it's a bit informal, like, can we still verify or find such asserts? Although, like, you are very much correct, I mean, the kind of probabilistic asserts that very much depends on, I mean, the user, or basically the programmer who's writing the probabilistic program as to what he wants to find. But I think, like, for now, we tried out, like, some well-known asserts, and can they work on those well-known asserts? Yes.
So, I mean, you had in your last slide a bunch of stuff that are still left to do. If you say you think about, some point in the future you're going to like write a thesis and defend your PhD, like, do you have a specific subset of those in mind for what will be in there, or is it all of those, or?
Okay, so I think, coming back here, I would like to focus more on points 2 and 3. I would say point number 1 is something which we have just started exploring, so we are not very sure as to what to do with point number 1. But for point 2 and 3, we already are trying to, like, improve upon maybe working with larger randomized programs, or there can be, like, tune the way fuzzing works in order for almost verification probability. Say, for example, we do have a project which runs almost verification for smart contracts. Can we have a fuzzer that can fuzz through smart contracts, which in almost verification? So I think point 2 and 3, I'll be focusing more on those, and point 1, it's still dicey. I'm not sure what is to be done.
So I have a number of probably naive practical questions about the fuzzing techniques. So, we talked about scale a moment ago, and if we talk about distant units with multiple parameters, how does scale deal with that when you're fuzzing multiple parameters to map out the space? Won't that become impractical?
Yeah, so that's actually a good question. So yeah, I mean, so in the third point, we're actually trying to, like, see which, like, can fuzzing be employed in such a way that, like, we can even talk about some of the parameters not being relevant for maybe for a given program, or like, even if there are parameters that are specific to fuzzing, like, can we say that, okay, like, use these values for fuzzing the program, or for, like, for with these parameters you should be driving the fuzzing so that the verification works well. So I think there is still some work there, like, both from the kind of program that we are fuzzing and the kind of fuzzing infrastructure that we are using. I think, yeah, there is some work to be done.
So is the idea that the fuzzing methods that are used are informed by data monitoring in the context?
Yes. So here, so instead of doing absolute black box fuzzing, we do want to, get some information from the program back while it is getting fuzzed. So maybe, I mean, just using some coverage metric, or like number of paths I covered or how many lines I'm covered, can we do something better? Yes, we are trying to explore into those facts, like, maybe, like, instead of saying how many paths, can we say how many branches I covered, or how many segments I've covered, and I define what segments I want to cover. Like, did I even reach there? So these are some of the things that we are trying to, like, improve when it's coming to fuzzing techniques. So it's the algorithm does not change, but the way we are trying to fuzz, the objective for what we're trying to fuzz changes.
Yeah, because I mean, at first glance, right, it flies in the face of Dijkstra's, absence of bugs
Yeah,
testing, right?
Yeah.
So in practical senses, right, you might survive this, but in real application, your program may die or return invalid things. Because when you say almost, what does almost mean, right?
okay. Yeah,
I mean, have you got a definition for what almost means?
okay, so and the way we defined almost in the very first work is that was modulo the fuzzing time that we had. So we did a study where we said that okay, like let's take simple regular programs, especially the benchmarks that were already present in code to win. Can we take those and see how well are we working on those? So there we found out that if we had a small timeout for the fuzzer, even then the fuzzer was actually able to find out what the counterexample for a given invariant is. However, we did find programs where the 10-second timeout did not work, where although from the fuzzer we had an invariant, but we later saw that okay that invariant is actually wrong. So that's where the almost part comes in. So what we studied is that if we increase the fuzzer timeout, maybe to like instead of like having like 10, 20, 30 seconds, can we fuzz it for maybe a couple of hours, maybe 2 or 3 hours or 4 hours, then in that case it would become harder for it to come up with an invariant, but it would not come up with some wrong invariant. So that metric improved when we started increasing the fuzzer timeout. However, coming up with a better invariant would require us to change the learner so that it can learn better and find a better invariant given we have such a long fuzzer timeout.
Right. So from research though, like what's the potential benefit here? Is it just kind of understanding how this might work, or are you actually suggesting that this has a practical benefit?
Yes, for practical benefits, what we're trying to say is that we are working towards automated verification. So most of these tools would not accept programs which have these concrete components. I mean, so either I will have to have some manual effort at writing out what the like how the concrete component behaves, or I'll have to use some other technique to like say what the specifications for these components are. So instead of doing any of those, can we still employ whatever I have and still verify the program? So over there, we found that okay, like Fuzzer could have a direct application to verification for such programs, and we started exploring that.
I'm seeing it, because I mean, the benefit I can see is that it would tell you when there were problems. But I mean, going back to Doctoral, right, it's never going to tell you that you can count on it.
Yes, yeah, I mean, it doesn't guarantee such things, yes, but I mean, uh, like, so in such cases, we will again have to resort back to the normal verification techniques, but then for those programs, it would not work because I have to give the logical specifications for all the concrete components that I have. So instead of that, can we like do something in the middle? That's what we are trying to find out.
So would one approach to claiming a benefit be to say that it's verified with certain input parameter data sets? Would that help?
Yes, absolutely. Yes. So or another better way to say it would be that okay, like we guarantee certain things would not happen, or maybe like in the domain or modulo these things the program is working fine or like it's verified. However, for I mean if we go beyond such parameters or such instances, then yeah, I mean we can't say it's verified or not.
Yes. Let me put it to you that, well, even if you proved it, you don't have a guarantee anyway. The proof always rests on undocumented assumptions, and who knows what the probability that those assumptions will hold in practice will be. So I certainly don't think that there's necessarily an issue here. one thing that occurs to me is that you've got complete control over the program that you're generating, which you're then fuzzing to try to falsify the invariant. And that means that you can, for instance, generate that program in such a way that you can get really useful feedback signals to help the fuzzing beyond just coverage, right? So I guess that's something you guys are thinking about already. Coverage is a pretty weak signal in some ways. The other thing that occurs to me is that you can then collect a whole bunch of statistics as you're fuzzing to, for instance, help you calculate what is the bias in the fuzzer that you're using, and then maybe use that probabilistic information to help you put bounds on your confidence that the invariant really is inductive, right? Normally you couldn't do this because you don't know what the bias is in the fuzzer and what inputs the program's being run on, but actually you guys can because you've generated your program, right? So you can collect whatever statistics you want and then go and do an analysis after the fact, right? And help you come up with some confidence intervals under some certain assumptions about what the input distribution to the program is going to be in practice, right? Anyway.
Yeah. Yes, absolutely. I think that would really be beneficial.
That sounds very cool. Do we have any final words, suggestions? No? Okay, let's thanks a minute again.
Thank you.